Hello, let's do electric fields applications. And so in this video I'm going to talk about some real life examples where electric fields are being used or created or have effects. So one of the most common uses of electric fields are in smoke precipitators, or chimneys that get rid of the ash and all the particulate matter that come out of furnaces. So we're not talking about your domestic fireplace, for example, but more in industry and big heat stacks like this and these guys here. So what they're trying to do is produce a chimney that doesn't have any particulate matter coming out of it, maybe just hot gases. And so how they work is by electric fields. Most of the smoke particles are things like carbon, various bits of residuals, but they can be charged, and how they're charged is they're put through a metal grid that's negatively charged, and so the droplets all pick up a negative charge, not the droplets, the particles. They then find themselves in an electric field, and the smoke particles that have a charge now are drawn towards either plates, the positive or the negative, depending on what charge they gain. And what happens is that these either turn off or they reverse their polarity just for a millisecond, and they cause some droplets to fall, particles to fall, and they get gathered in some scoops and get rid of. And so most of the smoke particles are taken out of the hot gases. And this is just an example of it. Now it's also used as a way of filtering air. So if you need a clean lab for making silicon chips or for doing medical work, you might use this to get rid of all the pollen and things that are in the air. So you send it through a pre-filter, and then you have this ionizing section where any particles get ionized, and then they get collected on positive and negative plates, and then there's an after filter. So quite a common technique used in industry and various applications. And this is just showing the same thing, just in another graphic. Lightning is obviously an example of electric fields, because the clouds must have a very strong electric field, and typically the cloud gets divided up. So you've probably seen big thunder clouds, and people have researched them into a lot of detail. And so you have positive charges, negative charges, positive charges. All this is swirling around in the hot thermals that are typical of your thunder clouds. Although here in Tasmania we seem to have we get some thunder clouds when it's a bit cool, but the hot air and the turbulence are all coming from the mainland and come across to Tasmania. And so this charge must dissipate, and it must dissipate to the ground eventually. And so that's how we get the lightning. The cloud builds up too much charge, wants to lose some of the charge to the earth, and so sends out a leader. That leader is then met by an upward leader, which usually most people don't see, but they've been recorded on videos and things, and if you're really careful, if you're lucky, you might even see it, and then it all starts to balance itself out with that massive amounts of electrons flowing. And the thunder is, of course, because the hot plasma is heating the air faster than the speed of sound, and so the gas, or heating the air so that the air particles move at faster than the speed of sound away, and so you get a sonic boom, and that's the thunder that we hear. And of course lightning can hit various objects. There's a plinth, and it's been struck by lightning and does a lot of damage. It always has. And here's a top of a cathedral. There's a piece of copper, but it didn't manage to, or it may be faulty, it may not be connected to the earth, and therefore when the lightning struck, it actually went through the rock and can cause all sorts of things like this, the bricks and concrete. It can cause lots of other damages. This is some animals that were near a ground strike, and they were killed by being electrocuted. I think they were near a fence, and you still hear stories of stock being killed when lightning strikes fences and it then jumps from the fence to the stock and can kill them. Not a nice way to go. This is when lightning's gone down the earth. Most houses have an earth wire, and it's blown out the concrete there and some of the steel reinforcing. And this is an example of lightning where it's followed a pipe underground and caused all the water and stuff in the pipe to expand into steam and burst the pipe and leaves a rupture like that. So lightning is pretty serious business. People even go fishing, and this was a carbon fibre rod which acted like a lightning conductor and got frizzled into this stuff. I think the fishermen survived. And a tree being struck by lightning is a fairly common occurrence. Sometimes they splinter and disintegrate, sometimes they have scars like this. What do we got here? Okay, and so most tall buildings will have lightning conductors on their roof, but this is a bit of a fail in that here's some chimneys, there's the lightning conductor, and the lightning actually hit the highest point, which it would, because generally speaking lightning finds the path of least resistance to the earth. So that was a bit of a fail. And here's a picture of some lightning on Sydney Harbour hitting a boat, and that's the boat that it actually hit, and it did a fair bit of welding at the end of the mast. Pretty spectacular. And during a lightning storm, lots of strikes can hit. Typically lightning will hit high objects, because again it's trying to find the path of least resistance, and that's why it has this spidery effect, because it's working its way through the molecules of the air, and it has that effect. Planes can get hit by lightning, which is always a worry. This is probably a very extreme example. Well, I'll show you an even more extreme one shortly. Usually planes would act sort of like Faraday cages and pretty much get struck by lightning, and are designed to cope with the lightning strike and dissipate it, and all the electronics should be protected. So this was a fairly rare occurrence. Planes do get struck by lightning all the time. Generally speaking, most pilots try to avoid thunderstorms. This plane was struck by lightning and it completely disintegrated that part of the wing. It managed to land, clearly, but fairly lucky. Volcanoes can put on spectacular lightning shows because all these hot gases full of ash and charge, the ash is charged particles, and they're swirling around, and they can put on some spectacular shows. This is one of the ones recently, a couple of years ago, in Iceland, and people love to take photographs for them because they're just like, how good does it get? You have an erupting volcano, which is pretty spectacular, and then you get this massive light show from lightning and some spectacular photos. People can get struck by lightning. This girl got struck by lightning, and these are the clothes that she was wearing, and she's got a scar on her chest there. And of course the most famous person struck by lightning is of course Harry Potter. This person got struck by lightning as well, and you can see the scars. So a lot of people survive being struck by lightning. It's a bit of a lottery, depending on where the strike actually, whether it goes along your surface, as in this case, or through your body, and what organs it hits, whether or not you survive it or not. Now in some areas, particularly in America, where there's a lot of lightning, this campus has put on lightning detectors. So this is a little mirrored dish that whenever there's lightning, this sensor detects it, and it sends off alarms, because they have so many lightning strikes that to protect their students, they have lightning alarms, and they have lightning rods, and they detect, and sirens go off whenever there's too much lightning. And this is a lightning conductor for a light at an airport. So this light is on a pillar, it's standing above the ground, so it's a prime target for being struck, and it's metal and it's got wires, so it's a prime target to be struck by lightning. And so they put a conductor on it so that this part gets struck and the charge runs down the outside of the pole and dissipates. People can make artwork. This is some spectacular artwork called Lynchburg figures, and I'll try and put a video on the OneNote to show you how these are made. There's also a little video which is fairly low quality of a minivan being struck. I'll actually go on YouTube and see if there's any more interesting ones, and I'll put some on our OneNote. Now, ion engines, now there's a whole lot of words, so I wouldn't mind if you just pause this and read that if it's not too small. Ion engines are replacing chemical engines as to be used on rockets to send off space probes and various things. And they work by using electric fields. They accelerate by sending ions out the back of them. Hence they're called ion engines. And most recently one called Smart 1 was fired by the European Space Agency, and it went off to the moon and then circled the moon, did some experiments and stuff, and then they crashed it into the moon because they didn't want to come back. But it was the first major use of an ion engine, and I'll put some of these videos onto the OneNote, and you can have a look and learn a bit more about ion engines. And so this is again, pause all these and just have a read of them if you can. Hopefully the text isn't too small. And so what they're doing is, let's get my animation over here. There we go, look at that. So this is an ion engine versus a chemical engine, and this is our chemical engine and that's our ion engine. And an ion engine doesn't have as much thrust, so it's not instantaneously powerful, but here you can see the chemical engine has already run out of fuel, reached its maximum speed, and then travels at constant speed, whereas the ion engine is slowly using its fuel, slowly accelerating, but is using a lot less fuel, and now it's going to overtake, yay, the chemical rocket, and it's still accelerating, so it can get faster and faster and faster whilst that engine's firing, and takes away. So this is why ion engines are being proposed for lots of deep space probes and things like that, and even for Mars voyages and things. So how do they work? This is a very simple one. You have your chamber, you have an electric field, you make your ions, and then you eject them out by the particles experiencing a force in an electric field. Basically, I've got a better graphic coming up. Here we are. So what they do is, usually the ions are not electrons, but they're xenon, and so the rocket has to carry a small amount of xenon, but the rest of the rocket can be powered by solar panels or various other ways, and once the xeons are used up, that's enough. Now they have proposed, of course, collecting their own particles, because they could do that from all the particles that are in space, and then use those and extend the life of the engine. An interesting thing to note down here is there's got to be electrons ejected into the beam, so the whole rocket has to eject electrons, otherwise the rocket itself would build up too much charge and the positive ions would just be attracted back to the rocket and would defeat the purpose. So there's a little electron ejector to keep everything neutral. And this is what it looks like. There's not a person there for scale, but this one was pretty small. I think this is the Smart 1, and that's the actual engine outlet just there. And that's a graphic of what it would look like. Solar panels to keep the electricity. And so this is just saying that the xenon ions now are going 30 kilometers per second, and then by there that's 60,000 miles per hour, fairly quick. And another graphic showing you. Now this was the actual path that the Smart 1 probe took. It left Earth, orbited around whilst it was accelerating and getting faster and faster, then did this complicated, that's better, maneuver to eventually get to the moon. And the videos will show you this, but if you blink I think you miss it. but it's a very complicated procedure. Took a long time, whereas the Apollo missions pretty much went zoom straight to the moon. And this was what it did at the moon to actually get itself into a stable orbit. So I'll put some videos on the one.